Okay, so in this video, we are going to go through what covalent bonding looks like in contrast to ionic bonding. So to name covalent compounds, we first have to understand what covalent bonds are. So this occurs when two elements are sharing electrons. And we've done some work with electronegativity, and really what this means is that one partner in the compound is not strong enough to fully steal electrons from another, so they must share. And if one is a little bit strong, then it might be an unequal sharing, which means that would be a polar covalent bond. Polar covalent really has to do with the idea that one ends up being slightly negatively charged and one ends up being slightly positively charged. So to kind of give you an idea of what that would look like, water is an excellent example of that. So water is H2O, which hopefully you know, but it has some extra electrons over here. And so what that means is that those extra electrons on this side mean that, let's try to erase, mean that the oxygen is going to carry a slightly negative charge on that side, just because there's so many electrons happening over there. And that means the hydrogens are going to end up with a slightly positive side. So when you look at it holistically, there's like a little mini charge on each side. That's what polar covalent means. Whereas nonpolar covalent means that there's an equal sharing between the two. So that would be nonpolar. There are no poles. This is usually found between two nonmetals. So if I go to the periodic table here, the nonmetals are the ones that are located kind of on the right side here of the staircase, so to speak, the nonmetals. They are all the green and this kind of bluish color here. And usually they end up being liquids or gases at room temperature. When you're looking at how the electrons are actually shared, it can be visualized with Lewis dot structures. So you can see hydrogen has 1 valence electron, chlorine has 7. And if we remember, this has to do with where they were found on the periodic table. So kind of if you haven't labeled your chart already, this has 1, this has 2, moving over we have 3 valence, 4 valence, 5, 6, 7, and these guys, the gases over on the end, have 8. And they're all trying to get to that magic 8 number. So with that said, chlorine just needs 1 more. So in order to get that 1 more, it's going to share with hydrogen. So you see how they're sharing here, and it kind of overlaps. That would be an example of a Lewis dot structure to go with it. Here's another example. If you had 2 hydrogens together, they're happy. They're that unique situation where having just 2 is totally fine. Here's what I was trying to draw earlier. Water. Oxygen has 6 valence electrons, and hydrogen only has 1. So that's when you end up with these extra oxygens here and here that yield that overall negative charge. And then as a result, these guys over here are positive. So this is an example of polar covalent bonds. And on the other side over here, since they're the same, this was an example of nonpolar bonds. So let's try to do some practice. I'll do 1 or 2 of these to kind of get you going. So F2, F is an element. If I look at the periodic table here, F is right here with number 9. So F has 7 valence electrons, and I have 2 of them. So I'm going to have 1F, 1, 2, 3, 4, 5, 6, 7. This wasn't the best. And I have another F. I should have put 1 over here. 1, 2, 3, 4, 5, 6, 7. So they each have 7. So what they end up needing to do here is share. They're going to share that extra 1 side that they didn't have complete. So when they share, those electrons end up acting for both. So 7, or this fluorine over here has 7 plus the one that it's borrowing sometimes. And this one has 7 plus the one that it's borrowing sometimes. So those count for both elements. I can do the same thing with oxygen, O3. So oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. And I can do the same thing over here. 1, 2, 3, 4, 5, 6. And another oxygen, 1, 2, 3, 4, 5, 6. So what ends up happening is they share electrons so that they end up having more in completing that octet. Sometimes they can have different elements as well. So NH3 is another one, and NH3 is a weird one, I will say, because N has 5. And I know this because when I go to the periodic table, N has 5. So with that said, I'm going to put it with 3 hydrogens. 1 here, so they can share. 1 here, so they can share. And 1 here, so that they can share. And nitrogen is actually okay with this. It has its what we call a lone pair. This is called a lone pair that's just going to be off by itself, and that's okay. You just kind of distribute the H's a little bit around. This would be another example of a polar situation because there's that extra pair. Whereas Cl4, carbon has 4 valence electrons. So what ends up happening is that each chlorine that has 7 ends up doing 1 around each. So you're going to end up with a Cl over here, 3. And sharing, you're going to end up with a Cl over here. And sharing, and you're going to end up with a Cl over here. So there's a few circumstances where it's fine to have a lone pair, but under most circumstances, you're going to want to try to make everyone happy. So that's kind of the gist of covalent drawing Lewis dot structures. When we get to the point of naming them, then it gets a little bit different. For these, the first element is going to stay the same. And the second element does get an "ide." So with that regard, it's the exact same as ionic, but there's kind of an extra step. For covalent bonding, you add on prefixes. So depending on how many of something you have, you're going to add on a prefix that ionic bonds don't necessarily need. So showing you what that looks like, here's the table of prefixes to tell you what to do and how many there are. So, for example, if I have dinitrogen, that means I have, di means 2, so I have 2 nitrogens. And then pentoxide, pent means 5, like a pentagram. So I have 5 oxygens. Notice how the name of the first element doesn't change, it's nitrogen. And then the oxide part doesn't change. The oxygen gets the ending cut off and turns into an "ide, just like ionic bonds. But then we add on those prefixes. So just by reading this, I know I have 2 nitrogens, 5 oxygens. So then when you put them together, it looks like this. One thing to note is that if there is only one of the first element, then we just don't put the prefix. You don't have to put mono in front of every possible thing. So we'll do a couple of examples of what this looks like, and I put the chart for you in the corner so that you would always have the ability to reference it. So carbon dioxide. Here, again, there's no prefix, so that leads me to believe I just have one of them. And then dioxide. Well, I know oxide is oxygen, and di means 2, so I'm just going to put a 2 there. Now I can go to the second one, sulfur. Since there's no prefix, there's only one of them, and dichloride. So sulfur is S, chloride is Cl, and I must have 2 of them. When I get here, I do have a prefix in front of both, so that's telling me how many I have. I somehow have 2 oxygens and 2 fluorines, that got turned into fluoride. You must need to know how to go the other way as well. So I have 2 nitrogens, so I gotta go di-nitrogen. And then I have 4 fluorines. So 4 is tetra. And then I also need to make sure that I change my ending from fluorine to fluoride. So dinitrogen tetrafluoride is N2F4. Moving on, I only have 1 chlorine, so I'm just going to put chlorine. And then I have 3, so tri, like a tricycle. Fluoride would be the name of this one. And then finally, I have tetra, so I have 4 phosphoruses, or excuse me, yes, phosphorus. Tetra, phosphorus, and then I have 10, so 10 is deca oxide. Remembering to change the ending to "ide." So these are similar to ionic, but you just have to add on those prefixes to both.